Hello and welcome to another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 3, Lesson 2 on the average rate of change. The average rate of change, which basically measures how fast a function's outputs are changing compared to the function's inputs over some interval, is an amazingly important measurement that we do with functions all the time. It allows us to compare how fast two different functions are growing. It also gives us a nice real-world context in terms of how quickly real-world phenomena are changing, most often with respect to time. So we're going to get into it today. We're going to review how to calculate the average rate of change and how to think about it. So let's jump right into the first exercise. All right. In this particular exercise, we've got the function f of x shown graphed to the right. All right, it's a nice function f of x sitting over here. Letter A is simple enough. It says evaluate each of the following based on the graph. So take a moment, pause the video, and figure out f of 0, f of 4, etc. All right, well, this is simple enough. We're just reading things off of a graph. F of 0 is equal to 1, right? F of 4 is 1, 2, 3, 4, 5, 6, 7. That's equal to 7. F of 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's equal to 10. And f of 13, wow, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's equal to 15. Now letter B says find the change in the function. Remember this notation, delta, right, change in, over each of the following intervals. Find this both by subtraction and show this on the graph. So anytime we're trying to figure out the change in y, right, that's always sort of y2 minus y1. So from 0 to 4, what I would do is I'd say the change in the function's value is 7 minus 1, or 6 units. And again, what that means, right, is that this has gone up by 6 units as we kind of measure those two heights. Here, right, we're going to say that the change in the function is equal to 10 minus 7, or 3, right? And that's then showing us this, the change being 3. Between these two values. Finally, here we have delta f is equal to 15 minus 10, or 5, right? And that's going to be that. Now, letter C is an important question. It says, why can't you simply compare the changes in f from part B to determine over which interval the function is changing the fastest? Why can't we do that? Why can't we just say, well, clearly it must be changing the fastest over the first interval because it increased by 6, and then the last interval because it increased by 5, and then the middle interval is only increasing by 3. Why can't we use that to talk about how fast the function is changing? Well, we can't do it because the domain intervals x's, the domain intervals aren't the same size. In other words, that first interval, right, where x is from 0 to 4, well, there delta x is 4. On the other hand, as x goes from 4 to 7, there delta x is 3. And then as x goes from 7 to 13, delta x is 6. These things aren't the same, right? So, it's silly. It would be silly to compare two people's weight gains if one person you're testing over the span of like a couple weeks and another person you're testing over the span of a couple years. It wouldn't make any sense to compare their weight gains. Not if you really want to see who's gaining weight the fastest, right? So now there's got to be a way to take that into account, and we're going to in the next part of this problem. So pause the video now and write down anything you need to. All right, let's clear it out. So now let's talk about average rate of change. Average rate of change is always the change in the function's value divided by the change in the input's values, right? And what that does is it gives us a ratio, right, that compares how fast the two are changing. So for instance, in letter I, delta f to delta x, if you remember on that last screen, what we had was that the change in f was 6, the change in x is 4, and therefore delta f to delta x is 3/2. All right, likewise, number 2, well, in that case, delta f to delta x, the change in f, if you recall, was 3 units over 3 units, so it's got an average rate of change of 1. In this last interval, delta f to delta x, my change in f was 5, my change in x was 6, then that's as far as we can reduce it. So let's talk about where it's going the fastest. Well, that's where it's going the fastest, right? And that's actually the second fastest, and that's the third fastest. Now, in each case, what we've really found are slopes, right? That is slope, right? Isn't slope the change in y divided by the change in x? But this isn't a line, right? But there are lines whose slopes we just calculated. For instance, the first one is the slope of that line. Okay, that's the one, whoops, I didn't want that. That's the one that has a slope of 3/2. Let me do the next line in a different color. Let's go with blue. The next line is that one. Let me kind of extend it a little bit this way. And that one is the one that has a slope of 1. One more. Let's go in green. The last line is the one that goes from this. That didn't work out very well. Let's try a green line. There we go. And then that last line is the one with the slope of 5/6. All right. Now, what does this measure? It really measures steepness, right? So that's what slope always measures, is steepness. So what we're really trying to do is kind of measure on average how steep the function is, how quickly the function's values are growing compared to how quickly the inputs are growing. Sorry about the messy picture. All right, well, I'm going to clear this out, so pause the video now and write down anything you need to. Okay, let's keep going. The average rate of change. For a function over the interval a to b, the function's average rate of change is calculated by doing the change in the function divided by the change in the input. All right, f of b minus f of a divided by b minus a. This is the classic slope formula. y2 minus y1 divided by x2 minus x1. It's truly the slope formula. All right, truly the slope formula, which is kind of cool. All right, it's a very kind of mechanical formula, and let's play around with it some. All right. Exercise 2. Consider the two functions f of x equals 5x plus 7 and g of x equals 2x squared plus 1. Calculate the average rate of change for both these functions over the following intervals. Do your work carefully and show the calculations that lead to your answers. So real quick, what I'm going to do is I'm going to just put a little divider in here so we've got a clear sense of space. Let's start with f of x. All right. And let's do it. You can be very mechanical about this. I like to calculate f of negative 2. That's going to be 5 times negative 2 plus 7. I'm going to do this in my head. That's negative 3. And I'm going to calculate f of 3. 5 times 3 plus 7, that's 15 plus 7 is 22. So the change in f divided by the change in x will be 22 minus negative 3 all over 3 minus negative 2. 25 divided by 5 is 5. All right. Let's do it for g of x. These calculations can be a little bit laborious, but it's not a bad thing, Okay, g of negative 2 is going to be 2 times negative 2 squared plus 1. That's going to be 4 times 2 is 8 plus 1 is 9. G of 3 will be 2 times 3 squared plus 1. 3 squared is 9 times 2 is 18 plus 1 is 19. So change in g divided by change in x will be 19 minus 9 divided by 3 minus negative 2. It's going to be 10 divided by 5 for an average rate of change of 2. All right, pause the video now. See if you can do the 2 average rates of change called for in, I guess, part 2. All right, let's take a look. Again, for f of x, we'll do f of 1. 5 times 1 plus 7 gives me 12. F of 5. 5 times 5 plus 7, 25 plus 7 gives me 32. Change in f divided by change in x. 32 minus 12 divided by 5 minus 1 gives me 20 divided by 4 gives me 5. All right, let's do g of x. Let's see, whoops, how about g of 1 will be 2 times 1 squared plus 1. 1 squared is 1, times 2 is 2, plus 1 is 3. Whew. And g of 5 will be 2 times 5 squared plus 1. 5 squared is 25, times 2 is 50, plus 1 is 51. So now we're ready. Delta g divided by delta x. 51 minus 3 divided by 5 minus 1 will give me 48 divided by 4, which will give me 12. Ooh. Letter B asks, the average rate of change for f was the same in both 1 and 2. Take a look at that, right? In both 1 and 2, the average rate of change for f was the same, but it was different for g. Why is that? And as a hint, let me just say that I could give you any interval and the average rate of change for f would be 5. So why is that? Did you figure it out? Something came up a lot in Common Core Algebra 1. F of x is a linear function whose average rate of change, I wish there was a simpler way of doing that, whose average rate of change is always a constant. That's what makes linear functions linear. All right? What makes a linear function linear is the fact that its average rate of change does not differ. It's always the same no matter what interval you give it, right? Which is why we can talk about the slope of a line, but we can't talk about the slope of a parabola. All right? Lines have only one average rate of change. The parabola that we were dealing with in function g of x, obviously its average rate of change is changing. All right, pause the video, write down anything you need to, and then we'll go on and we'll continue to work. Okay, here we go. Exercise 3. The table below represents a linear function. Good for us. Fill in the missing entries. Ooh, this is cool. So remember, this is a linear function. It's not directly proportional. It's a linear function. See if you can use what we just learned about to fill in the missing entries. This is a little bit challenging, so take your time. All right. Well, what do we know about linear functions? What we know is that the change in y divided by the change in x is a constant, not y divided by x. That was with that direct variation. The change in y divided by the change in x is a constant. So let's figure out what that is right here. All right, let's do that for a second. Well, the change in y would be 1 minus negative 5, right? 1 minus negative 5, all divided by 5 minus 1, which will be a positive 6 divided by 4, which will be 3/2. Now, what does that tell you? What it says is that for every increase of 2 in x, we get an increase of 3 in y, right? For every increase of 2 in x, we get an increase of 3 in y. Well, let's just take a look here. Here, right, x goes up by 6. All right, so what's y going to go up by? Well, let's see. If delta y divided by delta x is equal to 3 halves, and I don't know my change in y, but I know my change in x is 6, well, then my change in y has to be 3 halves times 6, and that's 9. So y's got to go up by 9. Again, it makes sense. I mean, I went up in x 3 times by 2, so I got to go up by 9. That means that's got to be a 10. Now watch this. I can do the same thing right here. Here, I see that my y goes up by 12, right? I just don't know my delta x. But I do know that the change in y to the change in x has to be 3 halves. So now I could do a little cross multiplying. 3 times my change in x would have to be 24. So my change in x would have to be 8. If that goes up by 12, x has to go up by 8, which means that's got to be 19. Ooh, this is a big one. 45 minus 19 is 26. Wow. All right, and then I got to find room for it over here. So again, I don't know what my change in y is, but I know my change in x is 26, and I know their ratio has to be 3 halves. So my change in y must be 3 halves times 26. That's got to be 39. And therefore, I'm going to add that 39 to the 22, and I must be at 61. All right? What this really relied on, though, is understanding that in a linear function, it's not that y divided by x is a constant. It's that the change in y divided by the change in x is a constant. And that can be kind of tricky. All right? Pause the video, write down anything you need to. All right, here we go. So today we reviewed the basic formula for how to calculate the average rate of change, and that formula is the slope formula. It's the change in y divided by the change in x. We also reviewed the idea that if you have a linear function, that change in y divided by that change in x is a constant. And we'll call that constant the slope of the line. All right? And we're going to work with slopes and lines a lot more in the next lesson. For now, though, let me just thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.